fluid statics. We start off with the problem. If I have a pipe and it comes up into the middle of a lake, and the pipe is round, so I'm showing the cross section of the pipe right here, you can see the side view of the top of the pipe is a red disc right there. And so that's sitting on the top of the pipe to prevent water from flowing in. So this is the pipe. That's our water. It's just sticking up into the pond or lake or something. This is a plane, so it's a flat surface. It's horizontal in orientation with the gravity. And we'd like to calculate the net downward force due to the fluid pressure. So all along the top of it, you have a hydrostatic pressure distribution, pressure, force per unit area pushing down, true? The net force down, I would think of replacing that distributed pressure distribution by a single equivalent resultant force, kind of like statics, down. What would be the magnitude of that resultant force? It would be the pressure at that location, and it's the same pressure if it's here, 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 all along that surface, true? And so that pressure is magnitude of rho g, and the height of the depth of the water where the plate is. This is gauge pressure. Atmospheric pressures all over, so typically you subtract out atmospheric pressure because it's all over. And they talk in fluid statics and hydrostatics, you talk about gauge pressure. And you multiply that pressure by the area, and our area in this case would be pi b squared, because b is the diameter, divided by 4. All that look reasonable? Now the next question is where would you apply that resultant force? Would you put it right in the middle? Sure, you'd put it right in the middle. And if you looked at the area, it'd be right there, true? That's where it would logically be applied, right in the middle of that plate. Let's change up the problem a little bit. So now I have, I'm comparing a round pipe and a triangular shaped pipe. A pipe that has a cross section that's a triangle. They don't make them, you can't buy them, but let's just go with it, okay? And it's the same distance b as the other one, but b was the diameter of a pipe, now it's the width of a triangular pipe. Okay? So if I asked you to solve it for this problem, you would get the pressure at the surface, which is the same rho g h1. To get the resultant force, you'd multiply by the area. So the pressure, let's say at the center of that plate, times the area. What is the area of this triangle? It's an equilateral triangle, so this distance is b as well, true? 1/2 base times height, where this time the base is equal to the height. So 1/2 b squared. This other one, we said it would be applied right in the middle. Would we apply that one in the middle for the correct placement of the resultant force? Would we apply it for now the triangular pipe right in the middle, or would we apply it a little to the right or a little to the left of the middle? Yeah. So you apply it a little bit to the left, true? And you recall from statics, when you're dealing with a triangle, that it's a 1/3, 2/3 relationship, right? So the location wouldn't be right there. It would be visually just a little bit over. And so this distance is 1/3 b, and this distance, I know I probably exaggerated, is 2/3 b. 2/3 down from the peak, or 1/3 up from the base. How many people remember 1/3? Yeah. Now, how did we get the 1/3? the moment of inertia, or another way of saying it, how did you calculate? Sum of forces. That's how we got the magnitude of F. FR, I'm trying to use some notation out of statics, the resultant force. You had a distributed load, you replaced it by a point load, and you chose the location of where to put that point load by a moment balance. Moment balance. And you could do a moment balance about any point, it'd be equivalent. Okay? Hopefully that jogs your memory a little bit. Now let's do, instead of a horizontal surface, planar surface, let's do a vertical. Let's do the side of a tank that's holding water. And so we're just thinking about this side right here, which color-coded red. Okay? And here I turn it and do a projection of that surface as if I'm looking this way at it. And so this distance may be the depth into the paper or into the board, true? And this distance is the height of the wall. Okay, does that help you get the orientation? Okay. Gauge pressure is 0 at the top, and the pressure increases linearly as I go down to the bottom. The pressure at the bottom is rho GH. Okay, so I have a distributed load. It's not a uniform, like a rectangular distributed load where we did have it in the previous problem, but now it's triangular distributed load, true? I'm going to calculate a resultant force, the magnitude of the resultant force, and then I'm going to choose the point of application on this wall, and the point of application, because of symmetry, would be half the way deep into the wall, but it would only be a height of 1/3 from the bottom or 2/3 from the top down, true? So I've kind of shown it where it should be placed, right in this vicinity. Hopefully that's 1/3, 2/3. Maybe it's not. Graphically, I'm probably off a little bit. What is the equation for the magnitude before I worry about the placement? The equation for F of R. The general formula is a pressure times an area. So some average pressure times the area. Think the average pressure. GH over 2. How many people like that? Is that right? One way to look at it is, what would this be if I had a distributed load that was everywhere, the pressure equal to the pressure at the bottom? If even at the top, I don't know how I'm going to get it, but even at the top, it was the pressure is equal to rho GH pushing that way. It would be a distributed load, right? Think about this. You just cut it in half. You just cut it in half. That's one way of thinking about it. If you look at this equation, it's like evaluating the pressure at the halfway mark. True? Right? It's as if it's evaluating the pressure halfway down, right here on this plate. Halfway down. What is that point called? The centroid of the area. The centroid of my planar area, true? Some people may say CG or just C for centroid, true? So you're going to evaluate the pressure average is the pressure at the centroid of the area. That's the average pressure when you have a planar surface. So this is centroid, or just simply C right there. Okay? Then I multiply by the area. In this case, what is the area? Is it W times H? Just like it was, the area. Now that we have the magnitude, F of R, where do we apply it? 1/3 up, right? And if you're looking at the projection, the red surface area, it'd be 1/3 up, just like we've written, and right in the middle. That's where we would apply it. And so they call this point not C for centroid. They call it CP for center of pressure. That's where you apply that resultant single force from the pressure distribution. Does that make sense? So on the side, that's what it would look like. It would look like this. F of R applied there. All of that makes sense? Yes or no? Please, please give me a thumbs up. Yeah. All right. So here I just said, will you take a distributed load, replace it with an equivalent force system? How many people took statics and used a book by the author named Hibbler? That's an excellent statics book. There's other excellent statics books out there too, but it's a very good book, and you can look at the chapter on fluid statics. He does a great job of explaining it. So let's now change it up a little bit, make the problem more difficult. I'm staying with the planar surface, a flat surface, true? It could be a circle, could be a rectangle, could be a triangle, could be ellipsoid, whatever the shape is can be general. But we have the side image is a straight line, and we're submerging it in a fluid, and here we have the orientation of the surface a little different. It's at some angle that's defined by phi, okay, from the horizontal, all right? Also, this point right here is the origin of a coordinate system that runs from y equal to 0 all the way down to where finally the plate starts. This plate starts maybe at y1. Then it ends at y2 and continues on. Do you see the coordinate system that's been introduced? Okay. Now, when we look at the pressure distribution on the top part of this surface, I didn't try to clear it out, but you just look at one side of it, we see that it looks like this, true? There's a couple observations about this pressure distribution. Everywhere it's perpendicular to the plate. That's one of the characteristics of hydrostatics. The pressure is always perpendicular to that solid surface that the fluid's in contact with, true? Okay. The next thing is the pressure at y1 is lower than the pressure at y2, shown by the magnitude or the length of that height of that pressure distribution, true? Can you tell me if what is the pressure at 1, the pressure at 1, would it be rho g, the depth at 1, h1? Yeah. And if that's h1, then I can replace it by rho g. h1 is going to be y1, the hypotenuse of a right triangle. I'm going to give everybody a minute here. I'm going to pause, actually. So I want to walk around and make sure you're awake and alert. And I want you to write down on the equation on your piece of paper what is right here. How can I replace h1 with something y1 and phi? It's not that hard, but I just want to see if we're awake. But this is rho g y2 times the sine. So now if I wanted to, I could express the pressure at any location going down. It's just going to be rho g times, I left off a y1, didn't I, on that one? Y times sine of phi. Now I got a pressure anywhere where y is between y1 and y2. All right? And it increases as y goes from y1 to y2. So what is going to be my resultant force? Well, this is the pressure as a function of y. What I want is one resultant force, which is unknown, times the area of my plate. I didn't show that red area, that third, that other view, but it's viewing it from this direction. Okay, you can imagine it's a rectangle. That's the area I'm talking about. It has to have a depth into the plate or into the sheet. is equal to the integral of the pressure times dA. True? And the dA is going to be the thickness, depth into the board, times dy if I actually wanted to make the computation. But we'll stop right there and we'll say, let's replace here and put the pressure as rho g sine of phi times y dA. So F of R times A. Everybody understand this equation? Where'd that equation come from again? It came from?
I was actually going to ask if you can go over that again.
Oh, okay. I anticipated confusion. Okay, somebody help me by answering my own question. Where did that equation come from? Yeah, I'm sorry. This is you're right. This is the pressure average times A. Thank you. That's the confusion, isn't it?
Yeah,
and now this is equal to F of R, the resultant force. True? Thank you very much. So I did have an error which was leading to confusion. I wonder how many other students were confused. Thank you for your bravery. All right, so the average pressure times the area gives me the resultant force. I want to calculate that resultant force, and then I want to calculate where to apply it for this case. So the resultant force is equal to this integral. Can I pull out rho? Can I pull out g? Can I pull out the sine of phi? It's the integral of y dA, true? If I can divide by a and multiply by a, did I change the equation any? Not really. But it helps me because what is the integral y dA divided by a? It's going to be yc or y bar, different notation, different statics textbooks, but it's the location of the centroid of the area. Okay, not the center of pressure, the centroid. So if I look at this, I come down right here, right in the middle, is y sub c. Or maybe we don't write it like that. Maybe we draw it like this. This is y sub c, the centroid of that area. So you take the centroid, you got the sine of phi, rho g, and then you have area. So what is all of this equal to? It's equal to some average pressure. It's average pressure times the area. That's all the average pressure. So the average pressure is the pressure evaluated at the centroid of the area. That's what it is. It's the pressure evaluated at the centroid of the area. Now that we know the magnitude, MAG, the magnitude of F of R, where's the correct placement for F of R? Now, it could be right in the middle. It could be 1/3 from this end up toward, and then 2/3 down. True? Okay. So let me kind of give you something to guess at. Guess at A. A says it's closer than 1/3 from the bottom. B says it's right at 1/3 from the bottom. Your answer, multiple choice guess C, or answer C, is that it's in between 1/3 and 1/2. Or answer D is it's right at the half mark. Or even if you want answer D, E, anywhere else. Anywhere else. I don't care. It's not E. All right? I want you to think about it, and now we'll give an opportunity to increase your blood pressure as I walk around. All right. So a lot of people said, I don't think it's as close as 1/3, and definitely not a half. It's somewhere in between, which is C, right? So it's C. All right. So very good. It's C. Now, okay, let's do this. The answer of is it closer to 1/3 or closer to a half, all depends. If I take this plate right here and I bring it up a little closer to the top, I don't change its length, but I bring it up closer to the surface, got it? And I bring it closer to the surface, got it? Does it shift closer to this point or this point? Now, the same thought experiment, take that plate and move it further and further and further and further and further down. Okay? Where does the resultant force need to be placed then? Let me insert a new page, and I'll try and explain this way. So I have the surface of the water, I have my slope, I put either the plate right here, that's how long the plate is, I've shrunk it, or I put it right here, same length, or I put it right here. See that? See where I've placed the plate? Okay. And now it's going to be a hard job. There's a half and there's a third. There's a half and a third and a half and a third. It's always between a half and a third. Okay. For this case, is the resultant force placed either at a half or a third? Which one? At A or B? At 1/3 from the bottom or half from the bottom? It does matter.
It doesn't really matter, does it?
No, it does matter. Because the distributed load in this case will be a triangular, purely triangular load. Purely triangular. True? And here, what did we say this load looked like? What did we say its name was? A what? Trapezoid, which is a combination of a rectangular and a triangular. Period, right? But when I go very, very, very deep, guess what? It's essentially a rectangle. True? It's got a little triangle on top. But up close to the surface, it's all triangle. True? So, when it was all triangle, the resultant force was a lot lower in magnitude, but where was it placed? At a third. It was placed right at a third. Right there. All right? If it's almost all rectangle, where is it placed? Very, very close to a half. So you're placed in between. I can't say real fast where exactly it is. I got to compare depths and angles and how long the plate is. True? Make sense? All right. So now I go back to this slide and I have the tough job now is give me an equation for where I apply it. So we're not going to apply it at y sub c, we're going to apply it at y sub p. That's the name of where we're going to apply it. Where it's going to be applied at, I need to clean this up some. Where it's going to be applied at, let me try and draw it like this. Okay, that's f of r. We know its magnitude, true. And it's going to be applied at y sub p. What was the name of y sub p? Center of pressure, right? And the y sub c? Centroid, and they're different. They're slightly different. Okay, now, how do I determine, going back to my statics course, where I place the resultant force replacing a distributed load? Not the sum of the forces in x, not the sum of the moments. Oh, yes, it is the sum of the moments, isn't it? It's the sum of the moments. So what I do is I say, I'm going to do the sum of the moments about any point. And I'm going to do it around point O. That's why the textbook point O is introduced. It's the origin. It's where y starts, that coordinate system y is 0. And that has to be the same, okay? So the resultant force, F of r, applied at y sub p, the distance from O, got it? And it's perpendicular, true? It's perpendicular, so it's just the two magnitudes times each other, the force times the distance. That has to be equivalent to the distributed loads moment. Well, how do I get the distributed loads moment? Pardon?
You take each part.
take each part, break it into itty-bitty little parts. That's right. So it would be the sum, or the integral, over the pressure times the area. That gives me a little dF. Pressure area is a little force, dF, multiplied by the distance from O. And they're always perpendicular as well. It's always right angle. True? Now I'm glad that we had the pressure worked out as a function of y. So we can substitute into there. Let me just rewrite that equation right here. So we have F of R applied at y sub p. This equation will give us what y sub p is equal to. That's what I'm using it for. Is equal to the integral of, I'm going to go ahead and, for space, I'm going to pull out rho g sine of phi. Then I'm going to have y times dA. True? So that's y squared dA. Do you see where both y's come from? One comes from the p, right there, and one comes from that moment arm distance. So it's y squared. Okay, if I multiply and divide by area, what is, actually forget that, just so you don't forget I said that. I just recall from statics, what is the integral of y squared dA? Moment of inertia, not inertia, but it's a area moment of inertia. That's what it is. True? How many people remember that term? Area moment of inertia. Its cousin is also the mass moment of inertia. True? So let me see, I may have it on this slide. There it is. So you have to recall area moments of inertia for different geometries. So maybe this was a rectangular area going back depth W into the plate, right? So it looked like something like this. I know I'm slanting it a little bit. Okay? And right here is the axis going through the C. What is C? The centroid of the area. True? And so in books, they'll often give us some shapes like this, and then they'll give us I sub x. What is I? Area moment of inertia. X symbol indicating it's what? About this axis. Sometimes they'll put it IXX, saying it's through the XX axis. Got it? Or ZZ or YY axis. Different books, different subscript syntax. And then sometimes they'll even put a C, meaning it's going right through the centroid. That XX axis is going through the centroid, right? But this book that I copied it from doesn't have XX comma C, but it's the same thing. And for this equation, it's 1/12 base times height of the rectangle cubed. Do you remember any 1/12 base height cubed? All right. Before we interrogate this too much, what are the units, the SI units for area moment of inertia? Meters, meters squared, meters to the 4th power. That's very unique, isn't it? Don't you remember the first time you were introduced to this variable? It's like, what? How can that be reasonable? Meters to the 4th? That sure doesn't make sense, right? Anybody remember another moment of inertia called the mass moment of inertia? In dynamics, maybe? What were the units in SI for the mass moment of inertia? Kilogram meter squared. True? Okay, but that's just hopefully put that new information, a reminder of this information in context of other information you have already from another course like dynamics. So if I have a rectangle that's shaped like this, and there's the x-axis through it, or if I have a rectangle that's shaped like this, and there's the x-axis, which one has a larger moment of inertia? The second one. More areas further away from the axis that you're interested in, true? Somebody says, that's great that you have it for this axis. I don't want it for that axis. I want it for this axis. How do you do it?
Why would you want it for that?
Because in this problem, we don't want it for that axis that goes through y sub c. We want it for this axis that goes through O. Parallel axis theorem. Remember? How many people threw away their Hibbler statics book? Bad, 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 bad. Go read it, reread it, true? So go reread that excellent textbook in its discussion of area moments of inertia and the development of the parallel axis theorem. Okay? But the parallel axis theorem, it says that the I about a brand new XX axis, okay? Let me just kind of write it like this, is equal to the I through the XX axis that has to go through the centroid plus something that's going to have units of meter to the fourth power. If you do anything which it's not meter to the fourth power, it's not dimensionally consistent. Your equation has to be consistent. So you can almost guess, but what I'm going to do is I'm going to let some people shine, because I'm going to pause, I'm going to walk around, and I'm going to see how many people write down the parallel axis theorem, and this is the part that I'm missing. All right? All right, so basically you have this axis. If I want to move it from this axis that goes through the centroid, has to go through the centroid. You introduce a distance often called d. That's the distance between the two parallel axes, true? And so it's d squared times the area. It gives you your units. How many people now say, deja vu, got it? True? D squared A? So in this case, if I come back here, I have I, x, comma, c through this point into the page. It's an axis. I want to shift it because I'm doing the moments around O. True? True? Or what I do see is that this really is already the area moment around O. That's what it is. It's the area moment around O. So we've got rho g sine of phi times I sub O, or maybe you write it like this, xxo, true? But what is xxo? It's equal to ixxc plus d squared a. What is d squared? The distance between the two. Now d is equal to y sub c. Y sub c squared. True? All right. F of r, y sub p. At this point, what can I replace f of r by rho g sine of phi y sub c a? Was that f of r? Yes? Yes. Okay, can I get rid of the rho's, the g's, the sine of phi's, right? All right. And so if I need to scoot down, I didn't want to really scoot down, but I have to. So what I find is that y sub p is equal to, I'm going to leave it over here, y sub ca is equal times y sub p is equal to ixxo plus y sub c squared a. Did we follow that algebra?
XXC?
C. You're right, it's a centroid, that's right, through C. So now I'll divide through, and so we get the location of the center of pressure has to be equal to y sub C plus the centroidal area moment of inertia divided by y sub CA. And that equation is in your equation sheet.
Y sub P, you said it's going to move closer to YC as the plate gets deeper. Right? So where is the depth in this equation?
Well, y sub C, well, first of all, if it's y sub, not really phi, but it's y sub C getting closer and closer up, right? Yeah.
How does that work if you have two, though? How that works when you do both of them?
Both what?
In statics, we always take like the rectangle and the triangle by itself.
Okay, I'll show you that. But this equation, it's full of mathematics. But this resultant force right here, this, I should have recopied it. F of R is equal to the pressure at the centroid times the area. That works for triangle, rectangle, or this load, which is a combination of both. It gives you the right magnitude. Once I know the right magnitude of the resultant force, I get the placement of it, and the placement's given by this equation. Let me just summarize here, and then I'm going to come on. But yes, it's gauge pressure. So we have a submerged planar surface, same orientation, location, start of the axis. We put the resultant force at a location known as the center of pressure, and it's calculated by first getting the pressure average, or the pressure at the centroid of the area. Rho G y sub C sine of phi gives us that, true? They multiply that pressure at the centroid by the area to get the resultant force. The location is given by the location of the centroid plus I sub C, which is the through the centroidal axis, divided by y sub CA. This is the equation that's in your equation sheet. So that's why it's in there. Okay. Now, let's do this. Okay, I'm going to skip this for a minute and come back to it. An alternative approach to solving the gate problem, where I have a distributed load, I bust that distributed load into a rectangular component and a triangular component, as I've color-coded here and here. And then for the rectangular component, I think about, okay, resultant force A applied right in the very middle. And then for the other shaded triangular component, a resultant force magnitude B, I have to calculate it. But I apply it 1/3 from the base, right? And then once I have both of those forces and their locations, I take those two force systems and collapse it into a single force system. And I still have to do a moment calculation, okay? So there's another extra step doing it. I like this way. It's just longer. All right. But let's go back and use our newly developed mathematical tools to analyze this problem. Calculate the force that the stop must exert on the bottom of the gate to hold the water back. So it's water. We know the mass density. It's gravity, earth, everything. 3 meters, you have a hinge. The gate is 4 meters tall, and there's a stop at the bottom. So if we do a free body diagram of the gate, we have the hinge, and I'm just going to show it as at point A, AY, and AX. Those are the resultant forces that act on that hinge to hold the gate top right there at that location. We're going to replace the distributed load by a point load, F of R, resultant hydrostatic force. It's purely in the x direction. and we have to know its location. We're going to have to work on its location. True? And the stop has a force S to hold it in place. True? Did I miss any forces? Yes, we could put a weight on the gate. But if you put the weight on the gate, you do the sum of the forces in the y, you just find that ace of y has to pull up with the weight down. Okay? But we need to find the location of it. It's going to be between a third and a half. All right? Okay. So to solve this problem, what do I need to do? Is I would get the magnitude of f of r first. How do I get the magnitude of f of r first? Get the average pressure, multiply it by the area. Where do I get the average pressure from? It's the pressure at the centroid of my area. So here is the centroid, C. The depth of the centroid is 3 plus what? Is 5, right? 3 plus 2 is 5. So the pressure is going to be rho of the water, G, H of the centroid times the area. So it's 1,000, 9.81. It's 5 meters. The area is 4 meters by, I'll just assume 1 meter depth. Okay, width of 1 meter. They didn't tell me it, so I'll just assume 1 meter. And when you run those numbers, the resultant force is 196.2 kilonewtons. That look reasonable? Somebody has a calculator, they can check me? Okay. Now, where do I apply it? Well, just want to use your equations. You apply it at the y sub p, which is equal to y sub c plus I xx comma c divided by y sub c area. True? We did all the math to get there. So, okay, so what is y sub c? It's equal to 5 meters. True? I need to know the cross section of this. It's a rectangle. True? So it's going to be 1/12 the base times height. True? So I should have drawn a 3D image of it. All right? Okay. Its hinge is right there. That's all hinge. True? And the stop operates on the bottom. 1/12 base. Base is my depth into the third dimension times height. What is my height cubed? 4 meters cubed. 4 meters cubed. So this depth into the board, we are just working with 1 meter because that's what we used right there, 1 meter depth. True? All right. So that becomes 1/12 times 1 times 4 cubed divided by y sub c is at 5 times the area. The area is 4 times 1. So we find that y sub p is equal to 5.2667 meters, meaning it's below 5. It's a little bit below 5. It's 5.2667. True? All right, so that gives me y sub p. So that's where it's applied at, right there. F of r applied at y sub p of 5.2667. Okay. Now, if I want to now go to this free body diagram, I want to do the sum of the moments around point A. That must equal to 0. If I do it around A, then A sub y, A sub x, and w contribute no moment. The only things that contribute moment are f of r times the distance from A. Well, I had to work to get it distance from O down. What is the distance from A? It's y sub p minus 3. So this is now equal to f of s, the force that the stop has to exert in the opposite direction, times 4. So what we find, this distance 2.2667, right? F of stop is equal to the resultant force times 2.2667 divided by 4. Close enough. Now let's go to curved surfaces that are submerged. And this is not easy. All right. So if we have a surface, let's just pick one, draw it out like this. And it goes down and we have a fluid up here. And we have a section of that curved surface. It starts here and it goes around to right here, okay? Maybe it's a funny curved shape of a door. All right? And this is the floor down here. And I want to know what is the resultant force on that curved surface. And I want to know where it should be placed, or its line of action. Okay? Because I need to typically do some free body diagram of that plate later, that curved surface later. So everything over in here is all fluid, true? So the way you solve for this type of problem is introduce an imaginary surface to call out a free body diagram of a chunk of water that has the curved surface as one of the edges. Cut. Cut. And there's my free body diagram. Fluid, fluid, and the best that I can do of reproducing this curved surface right there. All right? Now, that chunk of fluid is in equilibrium, true? It's in, some of the forces in the x have to equal 0, the sum of the forces in the y equal have to 0, and the sum of moments around any point have to equal 0, true? So if I look at it, there's a pressure distribution along the bottom, and it's all pushing up. Can you see that? What else do I have? A distributed load that doesn't have to be triangular or rectangular. It can be the combination because it's the pressure at this depth and then the pressure at that depth, and so it's distributed load pushing completely to the right. Make your cuts vertical and horizontal on your other two surfaces to capture your fluid to do the free body diagram of. Okay, next is I have the force that the gate exerts to hold it in place. It's like that force has a net resultant force applied to hold the water in place. And then we have one more. What do we have? Some weight of the fluid applied at the center of gravity, or the centroid of that area. And it's really the location of the weight that matters. Okay, so that's what we have. So if we can calculate FR there, then we turn it around and say, if we can calculate the force that the door or the gate exerts on the water to hold it in place, then equal and opposite means that's the force that the water, it's like negative FR, how's that? Negative FR is what the water exerts on the red plate. Equal and opposite. That's right. This is, when you do submerged curved surfaces, this is the recommended approach.
Okay. And what if you draw this?
Sure.
Thing, you would have the weight.
Sure. Yeah, we'll solve a problem, but yeah. Okay, let's kind of slug through a little bit. So that's how you solve a problem for a curved surface. What would you do with this distributed load at the bottom? Replace it by a point load, and you have to find out where you apply it. That one's easy, isn't it? It's going to be right in the middle of this length of line right there. True? The other one you have to do a lot of work, and we just did it, but we get that resultant. So this one is a force in the vertical. This is a force in the horizontal. We get that magnitude of the force in the horizontal and the location for where it's applied. Now the weight comes into play, true? So you have to deal with that as well. Once you have these and the locations, then you have F of R. The sum of the forces in the X direction have to equal to 0. So what do we get? F of H is equal to FRX, or F of H, the way I've drawn it, that's in the positive X. The way I've drawn it is in the negative X. You add it, and that's equal to 0. Okay? And then sum of the forces in the Y direction equal to 0. What do we have? We have the F of R and the Y plus weight. That's going down. And then we have F of B coming up. So probably should do this. Let that be a positive quantity. Let those both be positive quantities. And so now I put negative signs because they're in the negative direction, the negative Y as well as the negative X. So everything in here is a positive quantity. I've taken care of the signs in the negatives. True? Make sense? All right. Ready to solve a problem? Oops, not that one. I want to solve this one. So we have a long solid cylinder of radius 2 foot. So here's the radius, 2 foot. And its length is 5 foot. Well, where's its length? Into the board. And now it's given, it's specified. It's 5 foot into the board. It's hinged at point A. There's A. And it's an automatic gate. When the water level reaches 15 foot, so the water comes up to 15 foot, the cylindrical gate opens by turning about the hinge at point A. So this will actually rotate a little bit, opening up a little gap and letting water through. Determine the hydrostatic force acting on the cylinder. So what force pushes on the cylinder? Its line of action when the gate opens, and the weight of the cylinder. So 3 things. So right as it's starting to open, before, first of all, if there's no water, it's hinged right there, there has to be a reaction on the concrete below, true? And it's going to support it. But as the water level goes up, it's going to make it such that this reaction force, when it gets up to 15 foot, goes to 0. That's the point at which it lifts off. And now you have a little water coming out. The gate's opening. True? So at 15 foot water height, the reaction force right there is 0. Okay. 2 things we're going to do. We'll do a free body diagram of that cylinder. When you do a free body diagram of the cylinder, here is the weight of the cylinder. There's that reaction force, which is equal to 0. And we had a distributed hydrostatic load that goes all the way around like that. It's going to be not so high right here, and it'll be higher there. And it's always perpendicular to the surface area. Hydrostatic forces are always perpendicular to the surface area, right? That's a complicated distributed load. True? In order to simplify it, what we do is we pull out a fluid element like this and analyze the fluid element. Make sense? So let's do this. Pull out this fluid element that looks like this. True? Okay. For that fluid element, I'll have a distributed pressure load on the bottom pushing up. I'll have, I didn't draw that too well. I need to make it a little longer, force, like that. And then here, the same length as this is this length right there. And then it goes up to this So I have some distributed load on the left surface pushing to the right. All of these are pushing to the right, just like the pressure is pushing up from the bottom. True? All right. Now, do I have a weight of my fluid? Yeah. Okay. What else do I have? I have a force that the cylinder exerts on the fluid. And I want to get I need its magnitude and line of action. All right? All right. Well, if I look at this, all of the little pressure here is always perpendicular. The pressure is always perpendicular. The pressure is always perpendicular. The pressure is always perpendicular, right? If I just follow the trajectory of all these perpendiculars, where do they all go? Through the center of that cylinder. So the force goes to the center of the cylinder. I know it has to go through the center of the cylinder. Okay. I don't know its magnitude, but what I'll do is I'll characterize its orientation by an angle phi. So I know it's going through the center of that cylinder, and I'll characterize its orientation by an angle phi. Okay? So sometimes I'm thinking cylinder free body diagram, sometimes this wedge of water free body diagram. From the wedge of water, I'll get the magnitude of F and phi. Then I'll bring that over to the other free body diagram. Okay, let's continue on. So what I do is I replace it with the resultant force right here. What is the magnitude of F of H? That FH. And then this one is FV. Vertical, horizontal. Not too innovative. Just FH and FV. What's the magnitude of FH? It's the pressure at the centroid of that vertical surface. The centroid of that vertical surface is at what depth? What depth would that be? 14 meters. So it's going to be rho g, depth of 14 foot, not meters, right? 14 feet. That'll be the pressure at that area multiplied by the area. The area in this case is 2 foot by 5 foot. So it's 10 square foot of area. True? Makes sense? Let's do this. What is the weight density of liquid water? Sometimes use the gamma symbol for it. 62.4 lbf per cubic foot. 1 cubic foot, try and lift it, more than 50 pounds, 60 pounds, right? Probably half of you could lift it in the room, half of you probably would struggle and not want to lift it, right? Off the floor. You're saying, give me 2 of them, I'll lift them both, right? Okay, but anyway, so it's 62.4 times 14 times 10, and that'll give me units of pound force. Anybody want to run a number calculator? They can do that, okay? Now let's take a look at Y sub V, or F of V, sorry. It's the pressure at the centroid times its area. It's going to be rho g times a depth of 15 foot, true? And what is its area? Is it 2 times 5 foot? 10 foot. So instead of 14 foot, put in 15 foot and you'll get a larger F of V. True? All right. Let's do this now. What is the weight of the fluid? What's the weight of the fluid? It's going to be tough. So what I would do is I would say rho G, okay, times the volume. And the volume would be this volume subtract that volume. Does that make sense? So it would be the depth of 5 foot times the area of 2 foot times 2 foot minus this area right here, which is 1/4 pi r squared. It's a quarter of a circle, isn't it? So it's 1/4 pi 2 squared. 2 foot squared. I know I put a lot of feet up here. All units of length are feet. Now I stop. Does that make sense for the weight? Yeah, this is the weight of that water right in here. Right? So what I do is I have to get the area here. I get the area by getting this 2 foot by 2 foot and subtract off the black area to get the blue area. I'm doing this rectangle area. Okay, it's 5 foot deep, and I want this volume right there. So I do 2 foot by 2 foot, and then subtract off 1/4 of pi r squared, and then multiply by 5. Now once I have that weight, then I have the force, this force, this force. True? So I have them all. Now I do for this water wedge, I'm going to try and recycle some space right here. I can decompose this F of R into two components, F of R in the horizontal and F of R in the vertical. True? Okay. And I'm showing the correct direction to them. So I'm talking about positive quantities. So in the x direction, it shows us that F of R horizontal is equal to FH. And did somebody run a number for me on FH? What did you get for FH? 736? LBF? Yep. So FRH is 8736 LBF. True? Don't have it here. All right. Now let's do the next one. If I do the sum of the forces in the y, that gives me an equation that I have weight, well, F of RV down plus weight down is equal to FV up. So F of RV is equal to FV minus weight. What was F of V?
9,360.
LBF. And the weight? All right, so the weight we calculated to be 268 LBF. True? 268. Okay, you had a question? Gamma is a rho times G. It's equal to, that didn't look so good, is equal to rho times G. Rho is mass density, gamma is weight density. So instead of being in kilogram per cubic meter, it's in newtons per cubic meter. Instead of being in pound mass per cubic foot, that would be rho, pound force per cubic foot, gamma. So it's just a definition. Insert new. I thought I covered that before. Rho is mass density. In SI units, kilogram per cubic meter, USCS, lbm per cubic foot. True? That's rho, mass density. How about now weight density? Well, that's rho times g. And so that'll be newtons per cubic meter or pound force per cubic foot. For water, rho of water is 1,000 kilograms per cubic meter. True? Gamma of water, that's gamma, is 9810 newtons per meter cube. Or slip in a point right there and put a kilonewton right there. Almost 10 kilonewtons per cubic meter. Now the rho of water in USCS, 62.4 pound mass per cubic foot. The rho times g, or the gamma of water, 62.4 pound force per cubic foot. Look good? All right, let's go on. So now that I have the weight, blah, 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 can you calculate FRV for me, which is FV minus W? So 9360 minus 268. So it's 9,092. Got it. Thank you very much. So now I can calculate the magnitude of the resultant. I'm always running out of room, aren't I? So the FR is going to be FRH squared plus FRV squared square root 49,050 lbf. So there's the answer for part A, I think. So it's the hydrostatic force acting on the cylinder is a magnitude of 13,050. Okay. Now, next question is what is its line of action when the gate opens? So we already know it goes through, the line of action goes through the center of the cylinder. But what is the angle phi for it? So if we come over here, I'm going to try and recycle this illustration here. There is our center. This is the angle phi. That's actually, let me draw phi instead of theta. Phi. This angle is phi as well. And you have the hypotenuse maybe going this way for f of r. And you can decompose f of r into f r in the vertical and FR in the horizontal. We calculated this one to be 9092, this one to be 8736. So the inverse phi is the inverse tan or arctan of 9092 divided by 8736, and you calculate something. Do you get that number for me? Does all that make sense? Pardon?
Gonna have to work a couple.
Okay, work a couple of them. Yeah. And then now, that angle should be a little bit more than 45, right? It's 46 degrees. There you go, 46 degrees is that angle. Okay. Now the next question is, what is the weight of that cylinder? What is the weight of the cylinder? Well, I'm sorry, but I'm going to have to scroll down, and we go back to our free body diagram of the cylinder. Here's the complete cylinder. It has a weight in the center going down. It has a force like this that's on a line of action that goes through the center, and we just calculated phi at 46 degrees. And we just calculated the magnitude of F of R equal to 13,050. It's pinned at A. So we have a force A sub Y and A sub X acting on that free body diagram because of the pin. Is there anything for the reaction at this concrete wall that it rests on? No, it's lifting off, right? So R, the reaction at right here at this is 0. So just get rid of it. So if I want to calculate the weight, the unknown weight, how do I calculate it? You suggest do some of the moments about point A, because I don't want to calculate the reactions at A. And so if I do the sum of the moments about point A, they must equal to 0 to be in static equilibrium. So this little force right here is a challenge until you remember from statics the principle of transmissibility. What? The principle of transmissibility. Oh yes, the principle, good friends. Which means that I can conceptually place that force right here, anywhere along its line of action, and then decompose it into the force reaction that is the horizontal component and the force reaction in the vertical component. And then I say, does F of RH put a moment around point A? That's why we like the principle of transmissibility. But F of RV does. True? And we find that F of RV times its moment arm distance around point A, 2 foot, you got it, that was quick, is equal to the weight times its moment arm distance around point A, 2 foot. One's trying to make it spin clockwise, the other counterclockwise. The 2 feet cancel. They have the same moment arm distance. And we find that the weight is equal to F of RV, which we calculated, 9092 lbf. Now let's talk about buoyancy. 3 cheers. So Archimedes' principle, everybody's heard of it. But basically it says that there's a upward buoyancy force when you have an object that's submerged or even partially submerged in a fluid. And that upward buoyancy force goes through the centroid of the volume of the submerged solid. And if it's partially submerged, then you need to do the part, you get the centroid of the partially submerged section. If it's completely submerged, then it's just a centroid. That's it's upward direction, and it goes through the line through that centroid. And this other thing that is the magnitude of that buoyancy force upward is equal to the weight of the fluid that's displaced by the solid. The weight of the fluid that's displaced. Everybody heard that, seen that? Very good. How do they do that? Well, here's one way of doing that. Think of this. The solid sitting here and it displaces some fluid, right? And everywhere along there's always a perpendicular inward direction pressure force acting on it. True? Conceptually, find that surface area and have a same exact area of the solid volume traced out, but don't put the solid there. Conceptually, just have a fluid there. And ask yourself, if the fluid inside this enclosing circle surface is at rest, well, it is at rest, right? The fluid's not accelerating up or down or to the side or spinning in any way, shape, or form, right? And the fluid that's outside, that's exerting the normal pressure forces, doesn't know if it's exerting a pressure force on adjacent fluid or adjacent solid surface. True? So you ask yourself, do a free body diagram of this system which constitutes the fluid enclosed inside, right? The fluid that's enclosed. And do some of the forces in the y direction. Some of the forces in the y. What do we have? We have the weight of the fluid down. True. The net pressure is going to have a net upward force to keep that fluid chunk at equilibrium. And that net is going to be described by F of B. It's F of B up equal to W down. The buoyancy force is equal to the weight of the fluid that's enclosed. Now we take the same, replace it with the solid, and we say, well, the solid may have a much greater weight down, but it'll have the same buoyancy force up as what I calculated right here, because it's due to the external net force by the surrounding fluid. So the buoyancy force is just the weight of the fluid that's displaced. And its line of action always goes to the centroid for the displaced fluid.